Okay, so chapter 6 of CCNA 1, so the network layer. So we're going to talk about IP or Internet Protocol, well, in the generic terms. So, network layer protocols. Explain how network layer protocols and services support communications across data networks. We describe the purpose of a network layer in data communication. We explain why IPv4 protocol requires other layers to provide reliability. And we look at the role and major header fields of IPv4 and IPv6 packets. And so we also talk about routing. So we explain how routers enable end-to-end connectivity in a small, medium-sized business network. We look at how devices use routing tables to direct packets to a destination network. We'll compare a host routing table with a routing table in a router. We'll look at routers themselves and how they route traffic. And we'll start at configuring a Cisco router as well. So, network layer protocols. So again, having a look at the OSI model, network layer is layer 3. And so it provides services that allow end-to-end devices to exchange data across a network. The network layer uses 4 processes in order to provide end-to-end transport. So it does addressing of end devices, so IP addresses must be unique for identification purposes. It encapsulates it, so again it has its own header information that it puts on the data for transmission. And so basically there's a header that has source and destination IP addresses, among other information. There's routing itself, in where the routers will of course look at the destination address for the packet and direct that packet towards its destination. And of course decapsulation is what happens at the other end with a receiving machine when it receives a packet, and how it decapsulates it and interprets it. Okay, so there are several network layer protocols. However, you will rarely see anything but IPv4 or IPv6. So we don't talk about anything else in any great depth in this course, because these days they're pretty much irrelevant. So how do we encapsulate the IP layer? So of course we have a piece of data that's got a TCP or segment header, and that is all treated as data for the IP header, for the IP packet. And so the IP header itself has of course source and destination IP addresses, as well as other control information, and away you roll. So the IP header stays the same from the source to the destination host, while, as we discussed with layer 2 headers, they will change with each hop along the way, because they are the point-to-point services of whichever link it's going through at the moment, while IP keeps track of the entire trip from source to destination. So the process of encapsulating data layer by layer enables services at different layers to scale without affecting other layers. And then routers implement different network layer protocols concurrently over a network and use the network layer packet header for routing. So, of course, the IP packet is then encapsulated with layer 2 information, which of course is your layer 2 header, and often the data, and there's often a trailer behind it as well. So IP was designed as a protocol with low overhead. It provides only the functions required to deliver a packet from the source to the destination. An IP packet is sent to the destination without prior establishment of a connection. It was not designed to track and manage the flow of packets. If you need reliable transmission of data, IP is not going to do it. You need TCP, or the transport layer, to actually to make things reliable. So IP is a connectionless protocol, so there's no dedicated end-to-end connection is created before data is sent. It's a very similar process to sending someone a letter through snail mail. You don't have to warn them that you're sending them a letter, they'll just get it. And so senders do not know whether or not the destination is present, reachable, or functional before sending their packets. This feature contributes to the low overhead of IP, because they don't have to do as much. Now they call IP a best effort delivery protocol, which basically means it tries, but if it can't get it through, it will drop that packet and it will wait for typically TCP to tidy up the mess. So it does not guarantee that all packets sent will be received. It means that it does not have the capability to manage and recover from undelivered, corrupt, or out-of-sequence packets. If packets are missing or not in the correct order at the destination, upper layer protocol services must fix these problems. So IP is media independent, and so basically, no matter what physical and data link layer protocols you're running, IP doesn't particularly care as long as you can transmit the data for it. And so basically, it's independent from the media that carries that data. It's not its problem. It doesn't care if it's copper, fiber, wireless, whatever it might be. The OSI data link layer is responsible for taking that IP packet and preparing it for transmission. Network layer does have a maximum size of PDU, and that can be referred to as the maximum transmission unit, or MTU. Data link layer tells the network layer the MTU. Now, an IPv4 packet header. These are all the fields that are in it. Now, there are quite a few fields. We won't talk about all of them. But of course, version is interesting because we talk about IPv4 and IPv6, so that the information in there is certainly of interest. Differentiated services, or diffserv, is basically how you can prioritize traffic. So traffic like VoIP will normally go to the front of the queue. Time to live is another interesting field, and so basically it's decreased by 1 every time it goes through a router. If it goes through too many routers, the theory is it may well have traveled through a loop, and so it will actually be discarded as being invalid. And so, of course, protocol field, it needs to know what transport layer protocol it is delivering this data for. So, of course, the sending machine will know, and so it puts that field in, puts the value in the field there, and so the receiving machine will then know that it's either TCP or UDP typically. And of course, source and destination IPv4 addresses are of interest as well. Now, IPv4 was designed many years ago, and it was not really designed for the purpose it's being used for now. They had no idea when they designed it that the internet would be what it is, and so basically it's got problems. So its major problem is IP address depletion, and so there are 4 billion addresses. There's possible addresses, not all are available actually, but of course there's 7 billion humans on the planet or more, and so instantly we've got a problem. And of course, how many of us have just one IP address? Not many. We've all got a computer, a laptop, a phone, a tablet, all these things. So yes, we do need more than 7 billion addresses. So the internet routing table has been expanding because it was not particularly well organized. And so the routing table just kept getting larger and larger and larger. And also, one of the fixes to that address depletion, they actually noticed the address depletion in the early 90s. And so they created a fix called NAT, or Network Address Translation. And so that has given us another 20 years or so. But it does have its downsides. And so some protocols do not like running over NAT. And also it stops giving you end-to-end connectivity. And so fault-finding problems can be harder, among other things. So IPv6 was started in the early 90s, and so of course its major advantage is it's a 128-bit address as opposed to 32-bit, and so there are billions upon billions of addresses available, and so that's one good thing. And basically they have learnt their lessons of where IPv4 was optimal, I mean, and so they've actually improved the design so it would work better. And so there's less fields in the packet header in IPv6 than IPv4. Typically, there are some additional header sort of appendices that can be added. And of course, with all that addressing, you don't need NAT, and so you do have end-to-end connectivity. There are roughly enough IPv6 addresses for every grain of sand on Earth, so that's a lot of grains of sand, so we should be good for a while. So if you compare the headers, as you can see, there are less fields. Of course, the addresses are 4 times bigger, but they've sort of made up for that with less other information. And so of course, basically, that's where it is. And so hop limit is equivalent to time to live. Of course, the version field's the first thing, and so on. So it is certainly different, but it is actually the same size. So the advantages of IPv6 over v4 using the simplified header. So it's efficient for packet handling, it's hierarchical network architecture for routing efficiency, auto configuration for addresses, and elimination of the need for network address translation. So it's not just the header's advantage, these are many of the advantages of IPv6. So basically you've got the version, which of course is 6 now, so 0110 in binary. You've got traffic class as opposed to that differentiated services. You've got a flow label, again, which helps handling of the packets. Payload length is basically the size of the packet, and next header, basically sometimes there will be extra headers added, and so it will tell you what it is and what type of header. So it's also got the hop limit, as I said, that replaces TTL, and then we've got your source and destination IPv6 addresses. Okay, routing. So basically, all hosts actually, if they're on a network, need to make routing decisions, just that your normal hosts don't have as many choices as a router will normally have. And so basically, an important role of the network layer is to direct packets between hosts. A host can send a packet to itself. So you can use the loopback IP address of 127.0.0.1. You can, again, talk to your own address, which is whatever it might be on the network, your local network, or of course another host on the same network. And so again, they will talk directly to one another if they're on the same network. Or of course, you have a remote host where you have a router, a device on a different network, and so you actually have to use the router to get to it. The source IPv4 address and subnet mask is compared with the destination address and subnet mask in order to determine if the host is on the local network or a remote network. And so basically the forwarding decision is, if it's a local host on the same network, you can talk directly to it. If it's on a different network, you actually have to go via the router to get to that remote host. So the default gateway is the network device that can route traffic out to other networks. It is the router that routes traffic out of a local network. So this occurs when the destination host is not on the same local network as the sending host. The default gateway will know where to send the packet using its routing table. Well, it should, hopefully. The sending host does not need to know where to send the packet other than it's on a different network. I'll give it to the router. So using the default gateway, a host routing table usually includes a default gateway address, which is the router IP address for the network that the host is on. The host receives an IPv4 address for the default gateway from DHCP, or someone has manually typed it in. Having a default gateway configured creates a default route in the routing table of a host, which is the route the computer will send a packet to when it needs to contact a remote network. So you can actually have a look at the routing table on your PC. So of course this is a Windows PC that they're giving the example for. And so if you type in route print or netstat -r, it will actually show you the routing tables. The output looks roughly the same. And so basically you get an interface list of which interfaces you have, and then you have the routing table for IPv4 and then IPv6. And so, as you can see, the quad 0 network here, that is a default route. So to a network other than the ones I know about, this is the default route, and my gateway is that. All the rest on link means this host can talk directly to them. With other networks, of course, it's via the gateway. And of course, its local IP address is that. So, router packet forwarding decisions. When a router receives a packet destined for a remote network, the router has to look at its routing table to determine where to forward the packet. A router's routing table contains directly connected routes. These routes come from the active router interfaces configured. So if we're looking at this highlighted router here, we have 3 directly connected networks. The 2 Ethernet networks here and this serial link to the next router. And then we have remote routes. And so these routes come from remote networks connected to other routers. They are either configured manually, so static routes, or they're learned through dynamic routing protocol, so RIP or OSPF or whatever it might be. You can also type in a default route, and that's much the same as what the host uses, but the router can use it as well. And if your router hooks into an ISP, you don't need to exchange routes with an ISP. You can just put a default route in there saying, the rest of the world is via my ISP, and so away you roll. So that's for all routes you don't know. So the routing table on a Cisco router looks something like this, and so the command is show IP route. And so you have this first column here is actually how did we learn the information. And so D actually stands for EIGRP, which is a Cisco proprietary routing protocol. C means a directly connected network, and L means the local address on that network. And so that's what that /32 means, is that it's the host address. And so we've got 2 directly connected networks, and we've got a remote network we've learnt via EIGRP. Now, when it comes to networks learnt from EIGRP, it actually has a lot of extra information. So routing protocols do that. And so we have what's called the administrative distance or trustworthiness. And so the lower the number, the better. And then this after the slash is the metric. And so that's a measure of how far away it is via that route. And so the smaller the metric, the better the route. And so it's that one with the smallest metric would be the one that's in the routing table. And then it also gives you how long it is since it's been updated, that information was updated or last reliably sort of communicated with, and that's the outbound interface. That's the next hop interface. And so a router examines an incoming packet's header to determine the destination network. If there's a match, the packet is forwarded using the specified information in the routing table. Okay, so directly connected routing table entries. As I said, C means a directly connected network, and L means the local interface. And so, and the L will always be a /32 for IPv4. Remote route entries, as I said, D represents EIGRP because it uses an algorithm called dual. That's why they use the D. And then we have a destination network. This is the destination network we're talking about. And of course, /24 is its prefix length. 90, as I said, is its administrative distance or how trustworthy it is. Then it's the metric. And so that's over 1 million by the looks of it. Yes. And then next hop IP address, how long since we've been updated about that or communicated with that router that we learned it from, and what the outbound interface is. And so that's S000 in this case. Next hop IP address. When a packet arrives at a router destined for a remote network, it will send the packet to the next hop address corresponding to the destination network address in its routing table. For example, if the R1 router in the figure to the left receives a packet destined for the network 10110, it will look up its routing table. And so here, the first entry that we look at is that. And it will send that packet to the next hop IP address of 209.165.200.226. and out that serial 000 interface. Notice in the routing table, the default gateway address is not set. If the router receives a packet from a network that is in the routing table, it will not know where to send it, and it will drop it. So if there is a default route, it will actually say gateway of last resort is, and it would actually tell you what its default route is, basically. Okay, routers. So router is just a computer. It's a specialized computer. And so it has a CPU, it has an operating system, it has RAM, it has permanent storage, it has all those things that most computers have. Doesn't have a monitor plugged into it directly, I suppose, but other than that, it is basically a computer. So Cisco routers are designed to meet the needs of a wide variety of businesses and networks, and so you have branch routers, and so they're a bit smaller with a lower capacity, and then you have WAN ones, and then you have service provider ones, and so they get bigger and more expensive as they go. And so we'll look at branch routers, but the interface on branch routers and service provider routers is pretty much the same, as in the command line interface is the same. The service provider one is probably just going to have a much more powerful CPU, more storage, and probably a lot more network interfaces. Okay, so like computers, Cisco routers require a CPU to execute operating system commands, including system initialization, routing functions, and switching functions. The component highlighted in the figure is a CPU from a Cisco 1941, which is what we've got in our rack. It's got a heat sink on top, of course, so it can dissipate heat and basically pass it on to the air, and so of course it keeps it cool. The CPU requires an operating system to provide routing and switching functions. Most Cisco devices use the Cisco Internetwork Operating System, iOS, and no, Apple did not invent that term. Volatile memory. Basically, routers, of course, need to store stuff, some of it temporarily, some of it permanently, and so there's different types of storage on the router. And so volatile memory, or RAM, is exactly the same as RAM in a computer, and so it's used for working with data at the time. And then you have non-volatile memory, which means if the power goes out, it will still remember the stuff. And so RAM, of course, is your volatile stuff used to store applications, processes, data needed to be executed by the CPU, while ROM is basically your boot instructions and basically a way of binding the operating system and booting the router. NVRAM is non-volatile memory, and that's actually where we store the configuration file. And then there's flash, which is instead of what a computer would normally have as a hard drive, and so it's again permanent storage, and that's where the operating system is stored. Okay, so there are numerous types and models of routers. However, they all have the same general hardware, so all computers need a power supply. Translate that electricity coming in from 240 volts to often DC voltages. They will normally have a cooling fan to move air through the case and keep things cool. SD-RAM, synchronous dynamic RAM, of course that's your volatile RAM. And then NVRAM is pretty much like flash anyway. And of course there's a CPU, there's heat shields and advanced integration modules and things like that. So the backplane of the router. And so this is where all the interfaces are. And so again, this is a 1941. And so basically it has a whole pile of slots here that you can actually add extra interfaces into. And so it does make this what we call a modular router. You can add interfaces to it to change how it behaves. And then we'll also have some other ports in it built in. So there's an auxiliary port here. You can plug a modem into it and do remote management through it. Console port, which is normally where we use a console cable to do our initial config with it. And then there are gigabit ports that we use for your local area network connections, and you actually do have compact flash slots, so you can have extra storage on the computer. And there are USB ports here that you can actually add, again, a bit of storage, or you can transfer files into or out of the router. Now, Cisco routers, how do we configure them? And so there's two major processes. There's one is in-band and the other one is through the management port. So initially you will always use a management port, so console auxiliary port, normally console. The in-band interfaces, of course, are the live network interfaces, and so basically once it's been configured, it's got IP addressing, you can remotely connect to it. So with the management ports, you would normally use a console program to configure the device, and so it's a dedicated port, and you do your initial setup, or maybe if network connectivity has been lost, you would use a console port again. If you're using in-band remote management, you can use SSH or Telnet. SSH is a better option, does take some extra configuration, but it is encrypted and secure. So Telnet is plain text, and if someone intercepts it, even with a freebie like Wireshark, it will tell you exactly what username and password was used. So not secure at all. Okay, so the boot files. And so basically, as the router boots, the iOS image is stored in flash. Part of the boot process is to transfer it into RAM. And so that's the major wait for the boot process, if you ever waited for a router to boot. And so once that's done, it will then transfer a startup config that's in NVRAM into RAM as well. And so that's actually how the router can be configured after a boot. Of course, if it's a brand new router out of the box, it probably won't have a startup config. And so you'll actually have to configure it first and then save the running config to be the startup config. And so the three major phases of the boot process is you have the power on self-test or post. And so that, of course, is much the same as many computers. When it boots up, it just checks to make sure it's got all the hardware it needs to run. So it's got a CPU, RAM, other kinds of storage, and everything's working, basically. And then from there, you locate the operating system and load that into RAM. And so typically that will be from flash, but it can also be from a TFTP server. You can actually configure it that if the flash copy of the operating system has been corrupted somehow, it can actually transfer it over the network. That will not necessarily be a quick process, but it will work. And then configuration is NVRAM. It can actually, of course, that's the startup config can be transferred into the running config or RAM. If it can't find an NVRAM, it can search your TFTP server for it as well. Or, of course, console is you or I typing it in. Now, you can actually do a command called show version, and that will actually show you what version of the operating system is running. It will also tell you a lot of other things as well. So it will tell you about the hardware, so what CPU, how much RAM there is, how much flash there is, and things like that. It will also tell you things like what encryption is enabled on that particular version of the iOS as well. How do we configure a router? Okay, so basically we did talk about switch configuration a chapter or two ago, and so configuring a router is not hugely different, especially for most of the stuff that you did in the switch. The major difference is configuring the interfaces. With a switch, of course, it's not actually a layer 3 device. If you set an IP address, that is typically only for remote management reasons. But of course, a router is the boundary between networks, and so each interface on a router needs to have its own separate IP address, and so that's certainly where they do differ. The configuring ports is different between a switch and a router because the ports do different things. So configuring a router, again, as I said, is not greatly different. Enable will get you into privileged exec mode. Configure terminal will get you into global config mode, and so on and so forth. And so not greatly different. You can do a banner message of the day, of course, to say that authorized access only, and away you roll. But of course, the other things, the interfaces are different. Now, as we said on the switch, it was interface VLAN 1 typically that we configured. With a router, basically it's whatever physical interfaces are plugged into that router. So as you can see here, we've got G00, we've got G01, and we've got S000. And so these are the interfaces we're most likely to be configuring. And so here, to do that, interface gigabit 00, set an IP address, turn it on, and that's all you pretty much need to do. And so then you'd go into gig 01 and S000 and things like that, and away you'd roll. So of course, I think I have mentioned it before, the difference between routers and switches is router interfaces are off by default, while switch interfaces are on by default. And so, of course, with a router, you've got to do the no shutdown command to turn it on. So shutdown turns it off, no shutdown turns it on. So once you've configured your device, you can sort of check how things are going and if that configuration is working in the way you wished. And so you can do show IP interface brief. That will give you a listing of each interface that's available, and it will tell you details like IP addressing and its status and the like. Certainly handy information. Show IP route, we looked at earlier. It's a router. Its routing table is its bread and breakfast. That's its major purpose, and so making sure the routing table is correct is pretty important. Of course, you can do show interfaces. That will often give you a screen full of information per interface. So, yeah, you may or may not want that, but yeah. Now, of course, once you've got a gateway, you've got to tell your hosts who the gateway is. And so basically, for an end device or a host to communicate over the network, it must be configured with the correct IP address information as well, but it needs to have default gateway information. So the default gateway is only used when the host wants to send a packet to a device on another network, and so from PC1 to PC3 or 4 is when it'd have to use the router. Of course, if it's on the same network, and you can use the directly talk to it. And so basically, PC1's IP address is 192.168.10.10. The gateway's address is 10.1. It's also got 11.1. But this must be using that interface because this PC can only talk to hosts on the same network as it. So the gateway needs to be on the same network as it to be able to talk to it. Same here. PC3 needs to know that its own IP address is 192.168.11.10 and its router is 192.168.11.1. Now, switches also need to know who the router is because as far as layer 3 is concerned, most of the time they are just another host. And so you need to do the default IP default gateway command and then set the IP address of the router in there. As I said, it doesn't actually use that information in its primary purpose. It's just that if this person were wanting to remotely configure that switch, well, for that switch to reply to their messages, it needs to know who its gateway is because they're on different networks. Okay, so there are some activities for these two chapters. So there's 2 for chapter 5 and there's 4 for chapter 6. And of course, there are chapter tests as well. Okay, so that's pretty much the end of chapter 6. We've just got a summary. And so we've looked at routing, connectionless. So basically, IP is connectionless protocol. It's best effort. It will try, but it won't lose sleep about getting data through. It's meter independent, so it can go across pretty much any network from layer 1 and 2. It will have a maximum transmission unit, so the maximum size of a packet it can send. Fragmentation can happen where it actually has to chop it up. If there's has to go across a network that is got a smaller MTU, it can sometimes be chopped up. ICMP, I think we have mentioned before, Internet Control Message Protocol. That does work closely with IP. NAT, of course, is the patch that was done to make IPv4 addressing last until now. Loopback interface, of course, is how you can talk to your local machine. And the default gateway, of course, is what's used by hosts to talk to remote hosts. There's the logo, so we're finished. So I will be doing a demo for chapters 5 and 6 very shortly, so that should be on the internet soon. But yeah, have a nice day.